Okay, let's try this again. Here we have a little simulation looking at the behavior in runtime, and here's time evolving, and what we have on the y-axis is the number of packets in flight from any given algorithm. And the black line here represents the ideal number of packets in flight, the bandwidth delay product. So if the number of packets in flight is less than that, that's bad because a scheme is not using the link enough. It needs to get at least to the bandwidth delay product to be using all the capacity that's there. But if the number of packets in flight is a lot more than that bandwidth delay product, that's bad too, because that means we're building up a large standing queue. So let's set up a scenario here. We can change the sort of link speed. How fast should we go today? Let's go like 10 megabits per second. So you can see that changes the bandwidth delay product. We should also change the buffer size here, the sort of queue length that's permissible inside the network, because it turns out TCP is very sensitive to that. Let's make it, I don't know, 1,500 kilobytes. All right, so now if we start up an old-fashioned sort of additive increase, multiple decrease TCP, let's look what happens. So we'll start it now. We go through this slow start algorithm, and then the number of packets, holy cow, keeps increasing until we hit that buffer. This blue line is the maximum capacity of the queue in the network. And now that we've had buffer overflow, TCP goes into this additive increase phase here, where the window is increasing by 1 every round trip time. So if we now start a second TCP, I'll start one now, we go through this slow start process, and you can see it's quite slow here, starting up, this sort of purple TCP. It's slow because the first TCP has put way too many packets in the network. So the sort of effective round trip time is very large. So now we get into this sort of quasi-equilibrium here, where the network is saturated. Both of these TCPs have more packets in the network than they should. They both have more packets in flight than the bandwidth delay product, but less than that buffer size. And so we have this sort of persistent unfairness, or the purple line is sort of persistently over the red line. Now how can this be? Kelly et al. Proved that TCP is asymptotically fair. Well, the fact is the asymptote can take a long time to get to. So if we speed up the simulation, we'll see the purple line is ahead of the red line, but they keep additively increasing here, and eventually we'll have the TCP sawtooth, where they have a multiplicative decrease in their window. And if we do this long enough, we see still this persistent unfairness. Eventually, there we go. Well, competitor needs to be, okay, there we go. So eventually, almost maybe 45 minutes in, they've converged to sort of a fair allocation of the throughput. So that's sort of the status quo. When the signal that TCP uses is this buffer overflow induced packet loss. So I see well anyway, okay. So let's turn off the TCPs, and now let's turn on one of these Remy optimized congestion control algorithms. This was optimized for between 3 and 300 megabits per second. So that was the model, is that the link speed is over that 100-fold range. And if we'll zoom in here, we'll zoom in. When we turn on the Remy designed congestion control protocol, here's what happens. So we go through this sort of fast start, I don't know what you call it, and then we end up in a sort of loop here, a limit cycle through the state space with this very high gain controller, as Jeff pointed out, where the number of packets in flight oscillates close to the ideal number. And if I start up a second Remy design controller right now, very quickly they start to share the link. So instead of that sort of long convergence time, the convergence time is much faster. But you see the behavior, it's better. They're sharing the link almost immediately. But we get this very sharp or high gain behavior. And if you look at what's happening in the state space, they're going over those very sharp edges that we saw. It's sort of like a thermostat turning on and off rapidly. So the behavior of these things at runtime is essentially this sequence of these high gain bang bang controllers.